Embraer jets are equipped with an X-band digital radar receiver transmitter and a flat plate antenna. The antenna's scanning angle is 120 degrees, 14 views per minute, or 60 degrees, 28 views per minute, and produces an 8-degree beam. Maximum display range is 300 nautical miles. The word radar stands for radio detection and ranging, and the device is based on the fact that some of the energy of radio waves is reflected by the objects they strike. The weather radar is a water detector, and it can detect only water in its liquid form. Radar energy transmitted is returned and provides scope reading. The harder it is raining, the more energy will be returned. Fog or shallow cloud formation will be ignored by the radar. The energy is simply absorbed and no return is provided. Frozen water, cirrus clouds, small hail, snow, is crystalline. Thus, the pilot will see no return at all. Let us know what the radar can see. Let's recall some basics of meteorology and radar image interpretation. You know, storm cells are not static or stable, but are in constant state of change. The heated air rises and cools to form cumulus clouds. As the cumulus stage continues to develop, precipitation forms in high portions of the cloud and falls. Precipitation signals the beginning of the mature stage and presence of a downdraft. Between these downdrafts, updraft continues at tremendous velocities. While a single thunderstorm seldom lasts more than an hour, a squall line can contain many storm cells developing and decaying over a much longer period. A single cell can start as a cumulus cloud, only 1 mile in diameter, rise to 1,500 feet, grow within 10 minutes to 5 miles in diameter, and rise to 60,000 feet or more. Therefore, radar should not be used to take flash pictures of weather, but to keep weather under continuous surveillance. The upper level of convective storms are the most dangerous because of the probability of violent wind shear and large hail. But hail and wind shear are not very reflective because they lack liquid water. Now check the illustration and see how rainfall rate affects weather indication on the radar. Color code for the various rainfall conditions are shown. As radar displays rain, it can also reveal the turbulence inside a thunderstorm. The areas of maximum turbulence occurs where the most abrupt changes from light or no rain to heavy rain occur. The areas of maximum turbulence are near the interfaces between updraft and downdraft. Nevertheless, the radar does not detect general turbulence. Some factors affect the resolution of the radar system. Increasing range will decrease radar return. The system compensates for this when in the automatic gain condition, pushing in on the gain control knob. This will provide a calibrated gain and should be used for en route weather condition. When radar radiation penetrates a dense storm, the radar energy is absorbed by the water. It results in the lessening or loss of all energy that attenuates the beam. In the RCT mode, radar incorporates attenuation compensation that continuously calibrate the display to targets to show the correct colors on the indicator. Although special compensation exists, weather radar should not be used for penetration of thunderstorm areas where the precipitation is heavy or moderate. The point where red level weather target calibration is no longer possible is highlighted by changing the background field from black to cyan. Cyan areas should be avoided. Any target detected inside a cyan area should be considered very dangerous. All targets in the cyan field are displayed as a magenta-colored fourth level precipitation. When the gain control is pulled out, the single rotary control allows the receiver's sensitivity to be decreased or increased manually as required for additional weather analysis in the weather and map modes. Caution is required to avoid reducing the gain to such a level that all radar display is eliminated. Selection of RCT or TGT alert overrides the variable gain. Flight level 200 defines the freezing altitude. The presence of water, in its liquid form, is less likely above this level. There may be water occasionally at higher altitudes, especially where there is heavy convective activity though. If, above the freezing altitude, the radar tilt is adjusted to capture weather buildups ahead of the aircraft and at the same level, probably little or no return will be shown on the radar scope. There is a recommended tilt adjustment technique in this case. This procedure is not to tilt the radar beam towards the top of the buildup, because this portion is a frozen portion, consisting of snow, hail, and cirrus clouds, but rather to the middle, where the radar can detect liquid water. Check the figures showing the relationship between tilt angle, flight altitude, and selected range. Observe the distance above and below airplane altitude that is illuminated by the radar antenna during level flight with 0-degree tilt angle. The range at which ground targets can be observed is affected by the curvature of the Earth, the distance from the aircraft to the horizon, and altitude above the ground. The approximate tilt setting for minimal ground target display is shown in the table. Operators should state their own policy regarding tilt setting. The following pieces of information are general guidelines to the matter. Takeoff and landing. On-ground operations required upward tilt to avoid ground returns. Initially, 15-degree setting will paint convective activity at 15,000 feet and 10 miles range. If tilt setting below 4 degrees is used for takeoff, some ground returns will be detected until passing 5,000 feet AGL. Climb, cruise. For overland operations, adjust tilt until ground targets appear at the display periphery. Storm cells displayed between half-scale and the outer edge of the display should be monitored, tilting periodically the antenna up and down and alternating range setting as necessary to see the total weather and the flight path. If altitude changes or a different range is selected, adjust the tilt control as required to minimize ground returns. When flying at low altitudes, rotate tilt upward frequently to avoid flying under a thunderstorm. The shorter the range, the greater the tilt. When flying at high altitudes, tilt downward frequently so as to avoid flying above storm tops. The shorter the range, the lowest the tilt angle. Pilots should learn about what is available from center, approach, and tower in terms of weather depiction capabilities. It is important for pilots to understand that calibration rates for image colors found on crew lounge weather radar depictions may not correlate with the rates that are associated with onboard weather color returns. However, some approach surveillance radar comes very close. In the event of a weather radar failure, or when in position for takeoff, and weather is in the approximate area, crews can query ATC for weather indications on their radar in terms of how many available lights are present, or there are any level 3 or higher returns in the direction of intended departure. Pinholes in the radome are responsible for water bubbles under the first layer of its structure. These bubbles do not block the radar emission, but they partially obstruct the flow beam, as a dirty glass obstructs the light, resulting in significant radar signal attenuation. External inspections can be performed to check the radome conditions and integrity. These are necessary to guarantee no water penetration on the radome's layers. If signs of water are encountered, the radome needs repairs or need to be replaced. Do not forget the radome is a component of the radar system and needs some care. The lightning stripes that are incorporated to the radome body are so important, but they charge the price. The main emission beam has 4 other secondary beams. One of these reflects on the lightning stripes and goes direct to the ground. When it returns reflected by the ground surface, it appears on the display as a green arc, and it is proportional as the conic rate of the radome. The narrower the radome is, the bigger will be the arc displayed. This is an airplane installation characteristic, not a radar fail. Now we are flying through a heavy rainfall in a specific altitude and speed, and the radar display disappears. This is not a radar fail. It happens because the water flows over the radome and covers it completely with a water film. This water film, or vapor, generated by the airplane speed can block the radar emission, and the red or black display can be shown. To avoid this problem, apply some hydrophobic coating product. Dirt and grease can impair the radar performance too. An inspection before flight can avoid and save much headache. One more tip. When on the ground and performing the test, a complete list of events and fault registration will appear. It does not mean that it is a radar fault. The system is displaying a list of the events that happened with the unit. If in the end of this list, radar OK appears, nothing is wrong with the radar unit, and it operates correctly. There is a radar fail message to indicate that this unit is out of order. Remember these tips regarding weather avoidance. Don't attempt to fly under a thunderstorm even if you can see through the other side. There may exist turbulence and wind shear. Avoid by at least 20 miles any thunderstorm identified as severe or giving an intense radar echo. Hail and hazardous turbulence may extend as much as 20 miles from the echo edge. It is better to avoid the whole thunderstorm area than to detour around individual storms unless they are scattered. Regard as extremely hazardous any thunderstorms with tops 35,000 feet or higher, whether the top is visually sighted or determined by radar. Playing within these gold rules, we can get the best from this valuable tool, and it can help us to avoid bad weather conditions and keep our flights safer and comfortable.